Hey guys, how's it going? In this video, we're going to talk about hyperparameter tuning, or also training the best machine learning model possible. We'll look at things like batch size, the number of epochs, the learning rate, different architectures, and we'll see how we can get a better and better model and see how these different hyperparameters are going to change the learning process. We'll look at the different metrics each time we train a model, and we'll look back and see what we can change to try and do better, or understand why it did worse. In this video, I won't be showing the whole machine learning process, definitely not most of the PyTorch code. If you want to see that and how we generated most of this notebook, aside from a few small changes, you can check the first video on PyTorch, which will be in the video description below. As you can see, this isn't quite Colab. If you want to run it on Colab, check the video description and play around with things as you follow me. But this is running on my local computer with CUDA and my good GPU installed. By the way, I'm going to ignore most of the code in this tutorial and just talk about the important pieces. Now, before we take a look at our hyperparameters, I just want to show you the model that we're making. The dataset that we're using is Fashion MNIST, and it looks like this, where each example is an image of 28 by 28 pixels. While it looks kind of colored here, it's actually just the color mapping. This is grayscale, so it's just one channel, and before the reshape, the image input is 1 by 28 by 28, because in PyTorch, the channels comes first. Now, along with each image is a label. That's what we're trying to get the model to predict. And so here, this is that same image there. It's a 1 by 28 by 28 image. That's what all of them are. And it's a label 9. Okay, so that means that of these 10 things here, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, which is 10 things. Since this label is 9, it's saying that this is an ankle boot. So we're trying to get the model that can take in an image, try to learn the mapping between what the image looks like and the label that it actually is. Now there's a couple important hyperparameters up here. Our batch size is currently set to 4, which means at a time, our GPU is going to take in 4 images in order to make an update for our model. The smaller the batch size, the less computation that needs to be performed, and therefore the faster the model can update. So in theory, it should learn faster the smaller the batch size. However, the smaller the batch size, you're getting a worse estimate of the gradient. And therefore, the higher the batch size, the more accurate the batches are actually going to inform the model. Therefore, there is a balance between speed, which is the smaller the batch size, and the accuracy, which is the higher the batch size. Somewhere on the range of 4, 8, 16, 32 images is probably ideal. We're starting with 4, and we'll play around with that a bit. And there's also an upper limit for the batch size. If you increase it too much, your GPU is only physically so large, and if you shove more data in it than it can fit, it's just going to give an error, and you may not see a great error. It might just seem like a bunch of stuff doesn't make sense. Try lowering the batch size, and you might get rid of that error. Now here's another hyperparameter, the learning rate. It really is the rate at which the model is learning. Of course, we saw that other things can affect that, like the batch size, but this is basically the multiplier of how big a step you want to take in what's hopefully the right direction to make the model better. So the smaller step you take, well, that's nice because you can almost guarantee that it is at least getting closer to the right answer. As in, if you had a very, very small learning rate and you let the model train forever, it's probably going to eventually find the best model that it can. Here there is another trade-off. The smaller the learning rate, the more accurate the model is probably going to be at the end of the training, but it's going to make it a lot slower. So the higher the learning rate, the faster the training. The lower the learning rate, the more accuracy. It's a very similar trade-off to the batch size. Again, somewhere in the middle, not a whole number because it's not images here. Here it is a multiplier. And generally, you're just going to see a 1 and then a certain amount of zeros after this decimal place. So it'll be like 0.1, 0.01, 0.001. That's what it is currently. If you have a high learning rate like this, you'll see the model initially learn something, but then it would have been better if you were to have it a little bit more zeros in front. We'll see how that works shortly. Now here's our model. In general, the more parameters or complexity you add, the better it's going to do on the training set. However, you might have an overfitting problem where you do really well in the training set, but on our validation set, which is where the model is looking at new data, it's what we actually care about, you might have a problem. And so the training accuracy might be a lot higher than the validation accuracy. That would be overfitting. For this particular model, we are using a convolutional neural network, which is very common for images. In this video, I don't really want to discuss exactly what the out channels or filters is, the kernel size, and there's also a stride. And here you'll see a pool with a window here. I don't want to talk too much about those details, but you will see a little bit as we play around with the model, how that's going to factor in. In general, stuff like this with the channels, the higher the number means you're adding parameters, you're adding complexity, and stuff like this window size, kernel size here, this pool window, it's just going to affect the spatial dimension, like the face of the image, but don't worry too much about that. We'll see where it matters. If you're watching this video and you also watched the previous, you'll see that this batch norm everywhere, at least these two spots for now, kind of appeared randomly. And you're just going to want it no matter what model that you use. It doesn't really matter. This is something that just is going to standardize the model, and there's a bit of a debate on where you're supposed to put it, but we are doing it after the convolution. And as we see in the forward function, it's actually after the ReLU as well. So basically what the model is doing is it does a convolution, and then it does a ReLU function, it does a batch norm, and then it does a pool. It does a convolution, a ReLU, a batch norm, a pool, and then we also added in, from the first video, an average pool here. And this 5x5, this is figured out through looking at the shape, but basically this is a global average pooling. It's something very common in TensorFlow, and they actually have a global average pooling layer. If you didn't understand any of that, don't worry, because that doesn't matter too much for the concept here. What I'm going to do is play around with the learning rate. Let's see how that affects the training. What I'm going to do is purposely make it a little bit too high. So say that you started with this learning rate. I'm going to run all of the cells, and let's see the training. Okay, so it starts at 11%, it goes to 11.6, 9.5, 9.2. It's already going down. Okay, so this is just clear evidence to me of one of two things. I know it's the learning rate because we just changed it and made it too high, but it could be one of two things technically, which is that the model is just really not fit to the problem at all. Like it's way underfitting, which means it's just not able to capture the pattern, or it's because the learning rate's too high. It is definitely the latter response. And so if we were to just shut this down every time, and then we go back and change the learning rate, what we're going to do is make it a little bit smaller. So now it's 0.01, and we will run that again. Okay, now it already starts at a much, much better rate, 56%, 69%, 73, 75.4. It's training very quickly because we have a relatively small batch size, and I have a very good GPU. If you're training on a Colab one, it might be a little bit slower, but it should still be pretty fast. Here we go. So it seems to be capping out maybe, no, it got to the 80%, okay, 79. And we see after the first epoch that the val accuracy is 83.2. Currently, this is actually a pretty good accuracy, so there's actually no problem with this at all. But I'm guessing that we can probably do better than this. I'll just wait until the end of this epoch, and then we can see and try to beat that accuracy, whatever we get. Okay, so yeah, the val accuracy actually got worse, and that's because maybe this is all the model can do, or the learning rate is too high. What I'm going to do is shut this down, and the best way to test if it's the learning rate, limiting it, is if we make it a little bit smaller. So we will add another 0 here, and I will restart the process. Okay, 46%, 66%, 71%, 73, and I should really be writing down what our best val accuracy was. I think it was about like 82%, something like that. So 82, let's see if we can try and beat 82%. Okay, it's looking like it's definitely slowing down around 79 to 80%. But again, as the learning rate gets smaller and smaller, it is just going to take longer to figure this out. Okay, so you can see the numbers are generally getting higher every single time. That's because, as we said, you're learning slower, but you should be learning better. And so the accuracy at the end of this is 81.2%. Let's see if we can beat that at the end of this epoch. Okay, so we beat that considerably. We're up to 84.1% now. So let's update our best. Our best val accuracy is 84.1. And it's looking like so far it's not really going to beat it. It's looking like it's getting stuck around the 84, maybe 85% region. And at the end of the third epoch, we see an 84.5 accuracy. Yeah, I mean, it got higher, but I think it's probably, oh, actually that got up to 87.1. I'll watch it for another epoch. Okay, so here we got up to an 85.9% compared to our 84.5. That was actually a considerable bump up, so I'm definitely going to let the model keep running there. Okay, at the end of that, it actually got worse, 85.8%. That's lower, so I'm going to shut that down and say that that is our current best. Now, you can see that, yeah, just the learning rate alone can have a drastic effect on these things. If optionally, you could try to make this learning rate even smaller. But what you'd almost certainly find is that it's just taking really long to probably get to the same result. So personally, I'm really happy with this learning rate. And technically, you might have to change it depending on the other changes that you do. But most likely, this is probably the learning rate that's going to work for all the models that we'll make. But we might try to change it later. Who knows? Now let's look at the batch size. Now we could actually make this as low as 1, and it's not as crazy as you might seem. This is actually a tactic used. So what do we expect to happen here? Well, there's probably going to be a speed up for each batch. You should just see it being computed faster, and so the model is going to make updates faster. But it's not necessarily actually going to learn better, because in order to estimate the gradients of the model to make its update, it might be a little bit too random. But we'll see. So we're going to run this and we'll take a look at what happens. Okay, so here it starts off with 36%, 61%. I can see it's actually going through the batches really quickly. I never actually talked about this, but it's basically printing every 500 batches, and it's just showing the accuracy across those 500 batches. So here it's going up steadily and pretty quickly. We'll see if we can randomly make it beat 85.9%. Although, to be honest, just decreasing the batch size, it's probably not going to randomly make the model a lot better. In fact, I wouldn't be surprised, and actually we're starting to see it. It might actually make the model a little bit worse, but I'll just wait a few epochs and we'll see what happens. And you're definitely going to see that there's just way more batches in general. Of course, if you have a batch size of 1, and I think our training set is 60,000 images, it might be 50,000. That means there's like 50,000 or 60,000 batches. Okay, so it looks like, yeah, there's 50,000 images in the training set. So we have 50,000 batches since our batches are of 1. On the last 500 batches, it got an accuracy of 83.4% on the training set. And on the validation, it was as low as 73%. Okay, so we actually seem to be having a bit of an overfitting problem here. It's overfitting to the training set in this case. But I don't really like this batch size because we were seeing better results before. This training accuracy is considerably higher than the validation accuracy was. And so because of that, we are going to, I guess we'll just move the batch size back to where it was before. There's no need to play around with this too much, but find something that works in around the 4 to 8 range. I'm going to choose 4 images because that's what we had at the beginning, and I'm not going to run that again. I will just stop it from doing anything. Actually, I guess for fun, I also want to show you what happens if you basically try to explode your GPU. It's not actually going to explode. A number that my GPU can probably not handle of images is 1024. I'm just picking a pretty large power of 2. If I go to try and run all of that, at some point, I'm pretty sure we are going to run into an error. So let's see where it is. It got the network, passed a batch in for an example, and it's trying to train the model. And actually, my GPU can handle batches of 1024 images, which is pretty absurd. I'm not sure if Colab can do that. I'm curious how high this can go, so I'm actually going to let this work. So let me change this to, I don't know, something crazy like 20,000. It doesn't have to be a power of 2, and I'll let that go. Okay, let's see if that runs into any errors, and it's starting to train. And actually, the GPU is handling images that size, and the accuracy is extremely small now, so it's really not working. The accuracy is definitely not there, but the GPU didn't explode. I'm not sure if maybe PyTorch is actually limiting how much is going into the GPU, or it's actually able to take this much. I'm not sure. But anyways, I'm not going to try to explode it anymore. That was an interesting experiment I've never done before by myself. So we are just going to leave the batch size at 4, definitely not 20,000. Okay, so we saw what happens when we play with the batch size as well as the learning rate. If the batch size is really high, it's going to mess it up. If the batch size is really low, it's probably also going to mess it up. Somewhere in the middle is a good idea. Learning rate, if the learning rate is too low, it's going to train super slow. And if the learning rate is super high, it's not going to train very well or very accurately. There's lots of other things that we can do, especially play around with this model. Now, it might be hard to remember because it was a little while ago, but our problem was not that the model was overfitting. The training accuracy and the validation accuracy were pretty close to each other, but they were getting stuck at about, we wrote it down, 85.9%, so at about 86% here. I'm willing to bet that for Fashion MNIST here, a pretty simple data set, possibly the most simple data set, we can get an accuracy a fair amount better than that. Now, what we're going to try here is definitely adding parameters to the model, or adding complexity. Now, the easiest to do that without changing really the architecture of our model is just to change the number of channels here. If you make this quite a bit bigger, we will change it to, say, 256. That means this has to go along with that as well, because the batch norm needs to be in the number of channels. So 256, 256. The in channels is going to be 256 down here. And we will make this, say, 512. This has to be 512 as well. And then this part is actually not going to change along with this, even though the number of channels changed here. It's going to be exactly the same over here. It's just that this in features is now going to be 512. With those changes made, adding more complexity to the model, adding more parameters, we are going to restart and run all. Now, again, the reason we did that is because the model was not overfitting. We just needed the model in general to capture a better pattern. And so if we add complexity into it, hopefully we see here both accuracies, the training accuracy and the validation are hopefully going to get higher than 86% here. Okay, we can see right away the training accuracy is already getting pretty high. It's getting 83%, 85% now. Okay, and we can see already at the end of our first epoch, we already have a new best validation accuracy. So clearly adding complexity into the model there was a good idea. Let's see how good this thing can do, because our learning rate is hopefully correct. Our batch size is hopefully correct, even for this change of architecture. And it's getting up to training accuracies of 86, 87%. And here you go, a new best already with this second epoch. 87.4% is now what we're trying to beat. We're going to let the model keep training. Okay, and now it's actually getting away from us because the training accuracy continued to get higher. It got up to about 88%, just a little bit higher, but then our validation accuracy went lower. So now what we're starting to see is two things. We're seeing a slight overfitting problem because the training accuracy is becoming a little bit higher than the validation accuracy. And we're also still seeing that the training accuracy the model in general is plateauing at about a 90% train accuracy. And so we kind of need to fix two problems here. We still need to add complexity into the model because hopefully we can get training accuracies better than 90%. But also we want our validation to not get so penalized here as we add complexity to the model. Because what's probably going to happen is if we add more complexity to the model, the validation accuracy, it might get even lower than 85, 86% here. So let's try and fight those two things. A really good way to add complexity to the model is just to add another linear layer here, because we're going straight from this average pooling and then just a flattened vector to one linear layer that takes in those 512 from the average, and then it changes that to the 10. But we can easily add a fully connected layer here. And so we will do self dot, we'll say FC1 for fully connected 1. It's going to take in features of 512. And yeah, we can just keep it at 512. That should be fine. So that way we don't have to change any of the numbers here. And then we're also going to have to change this down here. We will add in a x is equal to self.fc1 of x. And we're also going to want a ReLU activation. So we'll do the f.ReLU on the fully connected one. And we're going to not run that again, because I can almost guarantee you that a problem we're still going to have is some type of overfitting. Now, a way to combat overfitting, especially now that we have this new layer, is something called dropout, where if you watch my first video, I already explained what that is. But basically what it is that we add in for all of these 512, this is a 512 dimensional vector here. And for each of those spots, we're going to apply a probability to them, the same probability. Say there's a 30% chance that any of those 512 are going to drop. So with a 30% chance, it should be that 512 times 0.3 of them, so around, like 200 or whatever neurons on average are going to be dropped to 0. And what that does is that it allows the model to kind of learn more complex patterns without actually being super tied to particular patterns. It's a little complicated, but it allows to basically combat overfitting while adding complexity into the model via adding more parameters here. So we'll do a self dot, I'll just call it drop1 is equal to a neural network dot dropout. And then we specify that parameter p, that's the probability of any of them dropping out. We will start that off at, say, 0.1. Okay, so the lower the probability, the less combating it's going to do, the less involvement it's going to have on the model. And the higher probability, it's going to fight overfitting more, but it might also kind of screw with the model, because if you make too much of the neuron 0, well, that's just going to mess with it. Okay, but we're going to add that for now, and we're going to run that and watch the training. Okay, so remember, we're trying to beat this validation accuracy of 87.4%. I think there's actually a decent chance that this model is going to beat it, although it might be overfitting too much, I'm not sure. Here, it's quickly going to 80%, 82%. And okay, we're already getting a rival here. At the end of the first epoch, we have a validation accuracy of 86.3, and that actually is higher than the training accuracy. The reason for that is because the dropout is only applied during training, and so during evaluation, the dropout doesn't really do anything at all. There's no chance of anything dropping out, otherwise the model wouldn't work very well. And so sometimes when you do dropout, the validation accuracy will be higher than the training accuracy because of that. But as you see, it's still definitely going to go steadily up. And I have a pretty good feeling that at the end of this final batch here, that this is going to be a validation accuracy higher than what we've seen before, or at least higher than what we have above here. And it is 87.9. Okay, yep. So there you go. We have a new best, 87.9%. I'm going to let the model train for another epoch. Okay, in the training accuracy, we're getting up to 88, 89%. And the validation accuracy, I think it's going to be slightly higher. No, it's slightly lower, 87.7%. We're going to shut that down because it wasn't any better. But yeah, so that was pretty crazy. Actually, it looks like the training accuracy was going to continue to go up there. Maybe the model would have done better. But basically, I'm going to stop the video there. Now, if we go back to our model, there's a couple things that we could try. You could add more conv batch norm pool layers. You could add more linear layers. You could add a higher probability of dropout. If you added more linear layers, you could add another dropout with that. And there's also forms of regularization you can apply to these layers as well, although I'm not going to do that. It's not completely necessary in my opinion. I'm going to stop the video there. You could do all those different things, and I want you to try and beat our validation accuracy of whatever it was, 87.9%. If you keep a low enough learning rate and a big enough model, and you try enough, maybe you beat it first try. That would be great. I didn't try super hard, but I hope that you do. So if you liked the video, subscribe if you aren't already. Please drop a like. It would be really appreciated. And have a great day, guys. I hope this was helpful. Bye-bye.